Hello, calculus fans. Let's talk about another scientific application. This is also in physics. It's linear density. So the physical setup is, suppose that we have a long wire or a long rod. We're going to say that the wire is homogeneous if the linear density is uniform. Okay, what does that mean? It just means that the mass per unit length is constant. Now we're going to use this letter to represent mass per unit length. That's actually not the letter P, it's a Greek letter, rho, and that's usually used to measure various kinds of densities. Now, as it turns out, not all wires are homogeneous. They can have varying thicknesses. So let's suppose that the mass of the wire, as measured from the left endpoint to a point x, is m equals f of x. So you specify a value of x, that tells you how far along the wire you're going to measure. The function tells you what's the accumulated mass up to that point. Then the mass of the portion of the wire that lies between x1 and x2 is just delta m, and that's just f of x2 minus f of x1. Essentially, you're thinking about chopping the wire in two places. You chop the wire at x1 and then you chop the wire at x2, and you ask what is the mass of the wire in between those. That's given by this increment. Then we can ask about the average density of that portion of the wire. And we'll just get this. The average density is delta m over delta x. So that's the change in mass over the change in length. So we'll get f of x2 minus f of x1 all over x2 minus x1. Now we're going to let delta x go to 0. And now the limit that we get is going to define the linear density rho at x1. So this is the rate of change, that's the instantaneous rate of change of mass with respect to length. Now we can use the Leibniz symbology. We can say that the linear density is equal to the limit as delta x goes to 0 of the average density. And so this is a derivative. It's the derivative of the mass with respect to length. Well, let's do an example involving this. So let's say we're given a mass function for a wire. It's f of x equals log of 2x plus 1. And let's say this is only good between 0 and 6. So remember what this function gives us. It's the accumulated mass of how much mass we have up to a certain point. So in part A, we're going to ask for what's the average density of the wire between x equals 1 and x equals 3, and the linear density at x equals 2. That's what we want there. So linear density, that's the rate of change of the mass. Right now in part A, we don't need to use any calculus. The average density of that portion of the wire is just given to us using this expression here, the difference quotient. So we'll have delta m over delta x is equal to f of 3 minus f of 1 all over 3 minus 1. Because we're doing this between x equals 1 and x equals 3. So we're just plugging those values into the mass function that we started with. So we'll just get log 5 minus log 3 all over 2. If you work all that out, then we get this value here. I guess I never actually said what the units of measurement are, so we're going with kilograms for the mass, meters for the length. Okay, so this is an average density. Now in part B, we need to take a derivative. So the linear density at x equals 2 is going to be given to us by a derivative. So we're going to say rho, that's the linear density, is going to be dm by dx evaluated at x equals 2. So essentially we have to differentiate our mass function, that's this dude, and then we have to plug in x equals 2. So remember that the derivative of log of 2x plus 1 is just going to be 1 over the inside function, so that's 1 over 2x plus 1. But then we have to multiply by the derivative of the inside. That's the 2. Then when we plug in 2, we get 2/5. I don't have it on here, but the units of this are the same. It's still kilograms per meter. Okay, that's all for now.